welcome to this problem walkthrough. Today, we'll be tackling problem number 1213, intersection of three sorted arrays. This problem challenges us to find common elements across three sorted arrays, a valuable skill for mastering array manipulation and optimization techniques. Let's dive in. In this problem, we are tasked with finding the intersection of three sorted arrays. Specifically, you are given three integer arrays, ARR1, ARR2, and ARR3, each sorted in strictly increasing order. Your objective is to return a new array that contains only the integers that are present in all three of these arrays. The result must also be sorted in ascending order. For instance, if we have ARR1 as 1, 2, 3, 4, 5, ARR2 as 1, 2, 5, 7, 9, and ARR3 is 1, 3, 4, 5, 8, we want to identify the elements that are common to all three arrays and return them in sorted order. Let's now look at the outputs for some examples to better understand the requirements. For the first example, the input arrays are ARR1 equals 1, 2, 3, 4, 5, ARR2 equals 1, 2, 5, 7, 9, and ARR3 equals 1, 3, 4, 5, 8. The integers 1 and 5 are the only elements that are present in all three arrays. Therefore, the output is 1, 5. In contrast, for the second example, the input arrays are ARR1 equals 1, 2, 3, ARR2 equals 4, 5, 6, and ARR3 equals 7, 8, 9. Here, there are no common elements across the three arrays, so the output is an empty array, represented as. These examples demonstrate that the solution needs to carefully identify the shared integers while ensuring the result is correct and sorted. In the third example, the inputs are ARR1 equals 1, 2, 2, 3, ARR2 equals 2, 2, 3, 4, and ARR3 equals 2, 2, 3, 5. The integers 2 and 3 are the common elements found in all three arrays. Even though 2 appears multiple times in each array, our result includes it only once because the output must contain unique values. So, the output for this example is 2, 3. Additionally, the constraints for the problem include that the lengths of the arrays can go up to 10 cubed, and the elements within the arrays can range from 1 to 10 to the power of 4. This means that the solution should handle relatively large inputs efficiently. It's important to note that the arrays ARR1, ARR2, and ARR3 are always sorted in strictly increasing order. This property is key to designing an efficient solution. Regarding edge cases, if one or more of the input arrays are empty, the output should be an empty array since no intersection is possible. Similarly, if there are no common elements across the arrays, the output will also be empty. Even for arrays without duplicates, the output should still contain only unique values from the intersection. Lastly, the solution should be designed to handle large input sizes, up to 10 cubed elements per array, while maintaining efficiency. To begin solving this problem, the brute force approach is the most straightforward method to consider. The idea is simple. For each element in the first array, we check if it exists in the second array using a linear search. If it does, we then check if the same element exists in the third array. If it's found in all three arrays, we add it to our result list. While this method is intuitive, it's computationally expensive. The time complexity is O, n1 asterisk, n2 plus n3, where n1, n2, and n3 are the lengths of the three arrays. This is because for every element in the first array, we perform two linear searches, one in the second array and one in the third. Additionally, the space complexity is O1, since we don't use extra space beyond the result list. However, this approach has significant drawbacks, especially for large arrays, as it involves nested loops and repeated searches, which make it inefficient and slow in practice. To address the inefficiency of the brute force method, we can use an optimized approach that leverages the fact that the arrays are sorted. By using 3 pointers, one for each array, we can traverse the arrays in tandem and efficiently find the common elements. Here's how it works. We initialize the pointers to the start of each array and compare the elements they point to. If the elements are equal, they represent a common element, so we add it to the result and increment all 3 pointers. If the elements differ, we only increment the pointer pointing to the smallest element. This ensures that we skip over portions of the arrays that cannot possibly contain common elements. We continue this process until one of the pointers reaches the end of its array. This method avoids redundant comparisons and ensures forward progress by always moving at least one pointer. The sorted order of the arrays is key to enabling this efficient traversal. This three-pointer approach has a significant advantage in terms of time complexity. Each pointer traverses its array exactly once, so the overall time complexity is O, n1 plus n2 plus n3. The space complexity remains O1, since no additional data structures are used beyond the result list. These characteristics make the approach highly efficient for large input sizes. Additionally, the algorithm is simple and intuitive, minimizing redundant checks and making it easy to implement. However, the approach does have one drawback: it requires the arrays to be sorted. If the input arrays are unsorted, an initial sorting step would be required, which adds a time complexity of O, n1 log n1 plus n2 log n2 plus n3 log n3. Despite this, the optimized approach remains the clear choice when working with sorted arrays or when the cost of sorting is acceptable given the problem constraints. For this problem, we selected the optimized approach using 3 pointers due to its efficiency and simplicity. The key insight was recognizing that the sorted order of the arrays could be used to eliminate redundant comparisons, allowing us to traverse the arrays in linear time. This approach is significantly faster than the brute force method, especially for large inputs, and ensures clarity and scalability. That said, there are trade-offs to consider. While the three-pointer approach is optimal for already sorted arrays, it becomes less efficient if the arrays require sorting first due to the additional time complexity introduced by the sorting step. On the other hand, the brute force method, while easy to understand, is computationally impractical for larger arrays. Given the problem constraints, the three-pointer method achieves the best balance between performance and simplicity, making it the most suitable choice for this task. To solve the problem of finding the common elements across 3 arrays, our goal is to identify integers that appear in all 3 arrays, ARR1, ARR2, and ARR3. Each array is given as input, and we need to ensure that the result includes only those elements present in every single array. The brute force approach starts with a straightforward intuition. The idea is to systematically check each element in ARR1 to determine if it is also present in both ARR2 and ARR3. To do this, we first validate the inputs to ensure none of the arrays are empty. If any of the arrays are empty, we can immediately return an empty result since no common elements are possible. Once the inputs are validated, we initialize an empty list called result, which will eventually store all the elements that are common across the 3 arrays. This setup sets the stage for our brute force algorithm to process the arrays step by step. The next step in the brute force approach involves iterating through the first array, ARR1. For each element X in this array, we check if it is present in both ARR2 and ARR3. To perform these checks, we use linear searches. First, we loop through ARR2 to see if X exists in it. If we find X in ARR2, we then proceed to search for X in ARR3 using the same method. If X is found in both ARR2 and ARR3, we add it to the result list as it satisfies the condition of being common to all 3 arrays. After processing all elements of ARR1, the final step is to return the result list, which now holds all the common elements. While this approach is simple and intuitive, it relies heavily on repeated searches, which can make it inefficient for larger input sizes. When analyzing the brute force approach, we see that its time complexity can become a bottleneck for large arrays. Iterating through ARR1 takes n time, where n is the length of ARR1. For each element in ARR1, we perform linear searches in ARR2 and ARR3, which take m and k time, respectively, where m and k are the lengths of ARR2 and ARR3. As a result, the overall time complexity of this approach is n*m*k. This cubic growth makes the algorithm impractical for large arrays. Additionally, the algorithm does not take advantage of any structural properties of the arrays, such as whether they are sorted. There are also edge cases to consider. If any of the input arrays are empty, the result will be empty right away. Similarly, if no common elements exist among the arrays, the result will be an empty list. On the other hand, if all 3 arrays are identical, the result will contain all their unique elements. These insights highlight both the strengths and limitations of the brute force method. The brute force approach uses simple data structures to keep the implementation straightforward. The result list is used to store common elements identified during the process. Lists are a natural choice here because they are easy to work with and allow us to directly append elements as we find them. The input arrays themselves ARR1, ARR2, and ARR3 are also used directly without requiring additional space, making the implementation space efficient in this sense. However, the inefficiency of the brute force method leads us to consider optimized approaches. One such optimization involves sorting the arrays and using 3 pointers to traverse them simultaneously. This reduces the time complexity significantly, as we only need a single pass through all 3 arrays, resulting in a complexity of O, n plus m plus k. Another optimization leverages hashing. By storing elements of ARR2 and ARR3 in hash sets, we can achieve constant time lookups, reducing the search time for each element of ARR1. Both of these methods are much more efficient and address the limitations of the brute force approach while leveraging the structure of the data more effectively. The solution uses a 3-pointer technique to efficiently find the intersection of 3 sorted arrays. Let's break it down. 1. Initialization. 3 pointers I, j, and k are initialized to 0, corresponding to the current indices of ARR1, ARR2, and ARR3. A result list is initialized to store the intersection elements. 2. While loop, the loop continues until any one of the pointers exceeds the length of its respective array. This ensures we don't access out-of-bound indices. 3. Equality check. If the elements at the current indices of all 3 arrays are equal, ARR1, I, equals ARR2, j, equals ARR3, k, it means the element is common to all 3 arrays. We append it to the result list and increment all 3 pointers to move to the next elements. For pointer advancement, if the elements are not equal, we increment the pointer corresponding to the smallest element among the 3. This ensures that all arrays remain aligned, as the arrays are sorted in non-decreasing order. 5. Result return. Once the loop ends, the result list contains all elements common to all 3 arrays, which is returned as the output. This approach leverages the sorted order of the arrays, ensuring only a single pass through all 3 arrays with a time complexity of O, n1 plus n2 plus n3, where n1, n2, and n3 are the lengths of the respective arrays. This is significantly more efficient than a brute force approach, especially for larger arrays. Here, we start by importing the necessary libraries and defining our solution class. Inside it, we have the arrays intersection method, which takes 3 sorted integer arrays as input. To find the common elements in these arrays, we initialize 3 pointers, I, j, and k, all set to 0. These pointers will help us traverse each array. We also create a list integer called result to store the elements that are common across all 3 arrays. The main logic is implemented in a while loop that runs as long as all 3 pointers are within the bounds of their respective arrays. Within this loop, we check if the current elements pointed to by I, j, and k are equal. If they are, it means the current element is common to all 3 arrays, so we add it to the result list and increment all 3 pointers. If they are not equal, we determine which array has the smallest current element and increment the corresponding pointer to move forward. This ensures we maintain efficiency and only process the arrays in a single pass. Finally, once the loop completes and we have traversed the arrays, the method returns the result list containing all the common elements. This approach efficiently handles the problem by leveraging the fact that the input arrays are sorted, allowing us to use a 3-pointer technique. The time complexity of this solution is O, n, where n is the combined length of the arrays, as we only iterate through each element once. This makes the implementation both simple and optimal for the given constraints. Here, we're working through the first example, where the input arrays are ARR1 equals 1, 2, 3, 4, 5, ARR2 equals 1, 2, 5, 7, and ARR3 equals 1, 3, 4, 5, 6. We start by initializing 3 pointers I, j, and k to 0, and an empty list called result to store our output. The goal is to find all elements that are common to these 3 sorted arrays. First, we compare the elements at the current pointer positions, ARR1, 0, equals 1, ARR2, 0, equals 1, and ARR3, 0, equals 1. Since all 3 values are equal, we add 1 to the result and increment all 3 pointers. Now I, j, and k are all at position 1. Next, we compare ARR1, 1, equals 2, ARR2, 1, equals 2, and ARR3, 1, equals 3. This time, the values are not all equal, so we increment the pointer pointing to the smallest value, which is I because RR1, 1, is smaller than ARR3, 1. This process of comparing and incrementing continues until one or more pointers go out of bounds. By the time we finish, the only common elements we've found are 1 and 5, so our result is 1, 5. For the second example, the input arrays are ARR1 equals 1, 4, 7, ARR2 equals 2, 5, 8, and ARR3 equals 3, 6, 9. Again, we initialize the pointers I, j, k to 0 and start with an empty result. This time, as we go through the comparisons, we notice that no three elements are ever equal. For instance, the first comparison is ARR1, 0, equals 1, ARR2, 0, equals 2, and ARR3, 0, equals 3. Since ARR1, 0, is the smallest, we increment I. Then, in the next comparisons, we keep incrementing the pointer corresponding to the smallest value among the three current elements. This process continues until one of the pointers goes out of bounds. Since no common elements were found throughout the traversal, the result remains empty, and the output for this example is. Now, let's examine the third example where all three input arrays are identical. ARR1 equals 1, 2, 3, RR2 equals 1, 2, 3, and ARR3 equals 1, 2, 3. As usual, we initialize I, j, and k to 0 and start with an empty result. On the first comparison, we find that all three arrays have the value 1 at their current positions, so we add 1 to the result and increment all three pointers. Next, we compare the elements at the new positions. ARR1, 1 equals 2, ARR2, 1 equals 2, and ARR3, 1 equals 2. Again, all values are equal, so we append 2 to the result and increment the pointers. Similarly, we compare ARR1, 2 equals 3, RR2, 2 equals 3, and ARR3, 2 equals 3, append 3 to the result, and increment the pointers once more. At this point, all three pointers are out of bounds, so we terminate the loop. The final result contains all elements from the arrays 1, 2, 3. Here, we analyze the time complexity of the solution. The algorithm uses a three-pointer approach to efficiently find the intersection of three sorted arrays. Let's denote the lengths of the arrays as n_1, n_2, and n_3. The key idea is that each pointer moves forward depending on the comparisons between elements at their respective positions in the arrays. At each step of the while loop, one of the three pointers is increment, ensuring that no pointer moves backward. This means that in the worst case, each pointer traverses its entire array, leading to a maximum of n_1 plus n_2 plus n_3 iterations. Even in the best case, where all three arrays have identical elements in the same order, the pointers still move synchronously, resulting in the same asymptotic complexity. Therefore, the overall time complexity of this approach is n_1 plus n_2 plus n_3, regardless of the input configuration. Now, let's look at the space complexity of the solution. The algorithm requires additional space for a result list that stores the intersection of the three arrays. In the worst case, this list could contain all common elements across the arrays, and its size is denoted as k. Apart from this, the algorithm uses three pointers, one for each array, and a few constant space variables for computations. The space required for the pointers and other variables is negligible, contributing 1. Hence, the total additional space used by the algorithm is dominated by the result list, making the overall space complexity k. This is efficient because the space usage is directly proportional to the size of the intersection, which is the required output. Let's compare this optimized approach to a brute force solution. A naive method might involve iterating through each element in the first array and checking for its presence in the other two arrays. If the arrays are sorted, binary search could be used for these lookups, reducing the search time for each element. However, the time complexity for this brute force method would still be much higher, either n_1 asterisk n_2 asterisk n_3 for nested loops or n_1 asterisk log n_2 plus log n_3 with binary searches. In contrast, the three-pointer approach leverages the sorted property of the arrays to make linear passes through each, resulting in a vastly improved time complexity of n_1 plus n_2 plus n_3. Both methods require space proportional to the size of the intersection, k, but the optimized approach is clearly superior in terms of runtime efficiency. Finally, let's break down the time complexity into best, average, and worst cases. In the best case, the three arrays have identical elements in the same order, allowing the pointers to move in sync. Here, the loop runs for min, n_1, n_2, n_3 iterations, but the overall complexity still resolves to O, n_1 plus n_2 plus n_3. The average case occurs when the arrays have some common and some non-common elements. In this scenario, the pointers move based on comparisons, but each array is still traversed only once, maintaining the same time complexity. In the worst case, the arrays share no common elements, meaning each pointer iterates through its entire array. Even in this scenario, the total number of iterations is bounded by n_1 plus n_2 plus n_3. The mathematical proof for this is straightforward. At every step, at least one pointer advances, and no pointer can exceed the length of its array. The space complexity, dominated by the result list of size O, k, remains consistent across all cases. This analysis confirms that the algorithm is both time and space efficient under all input conditions. When working on problems like finding the intersection of three sorted arrays, there are several common mistakes to watch out for. One frequent error is not handling duplicates within the arrays. This can lead to incorrect results or duplicate entries in the output. To address this, you can use sets to automatically eliminate duplicates or explicitly check if an element is already included in the result. Another mistake is relying on inefficient nested loops, especially when dealing with large inputs. A brute force approach that uses three nested loops results in O, n-cubed, time complexity, which is far too slow for larger datasets. Instead, optimized methods like hash sets or the two-pointer approach can significantly reduce runtime. Finally, some implementations fail due to incorrect assumptions about sorting. The two-pointer technique only works when arrays are sorted, so you need to verify that the input is sorted first, or sorted as part of your pre-processing step. Without this, the logic of the two-pointer approach simply doesn't hold up, leading to incorrect results. Another area where mistakes often occur is in handling edge cases. If you don't account for scenarios where one or more arrays are empty, or if the arrays have unequal lengths, the code may crash or produce incorrect results. Adding checks for these edge cases at the start of your implementation ensures robustness. Misuse of hash maps or sets is another common pitfall. For example, improperly updating or accessing these data structures can lead to logic errors, resulting in missing or incorrect entries in the final output. To avoid this, carefully manage how you insert and retrieve data from these structures, and always test your code thoroughly to catch any hidden bugs. These mistakes might seem small, but they can have a big impact on the correctness and reliability of your solution. In an interview setting, it's important to go beyond just solving the problem. Focus on optimizations and demonstrate your ability to propose multiple solutions. For example, you can discuss the trade-offs between brute force, hash sets, and two-pointer approaches, highlighting their differences in time and space complexity. Clearly communicating your assumptions is another key aspect. If the arrays are sorted, you can explain how that simplifies the solution. If not, mention how sorting impacts the time complexity and why it might be necessary. Interviewers also appreciate when you proactively address edge cases, such as empty arrays, duplicates, or arrays of unequal lengths, as this shows thorough problem-solving skills. Finally, be prepared to justify the complexity analysis of your solution. For instance, you might highlight that a hash set approach runs in O, n plus m plus p, time, while sorting the arrays adds an O, n log n, overhead but could simplify the implementation. Being able to articulate these details clearly will leave a strong impression. There are also alternative approaches to solving this problem, each with its own trade-offs. Using hash sets is one method. By converting the arrays into sets and performing set intersection operations, you can achieve a time complexity of O, n plus m plus p, where n, m, and p are the lengths of the arrays. However, this approach has a higher space complexity, as it requires memory to store the sets. Another option is the two-pointer technique, which involves sorting all the arrays and then using three pointers to find common elements. While this method is efficient for sorted data with a time complexity of O, n log n plus m log m plus p log p, due to sorting, it requires an additional pre-processing step. Finally, there's the brute force approach, which compares each element of one array with all elements of the other two. Although simple to implement, this method is extremely inefficient for large inputs, with a time complexity of O(n*m*p). Choosing the right approach depends on the problem constraints, input size, and whether the arrays are already sorted. Great job on completing this problem. To summarize, we explored how to find the intersection of three sorted arrays. By leveraging the sorted nature of the arrays, we can optimize our solution for better performance. Remember to practice similar problems to strengthen your skills further. Thank you for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!